Today I'm going to talk to you about a project I've been working on called Root Cellar. It's actually not a single project with the source code right now. It's two separate projects that you put together in a certain way. You may or may not know I work on a project called Blevy. It's a full-text search library. And one interesting aspect of it is it has this pluggable KV layer. So you could use BoltDB, LevelDB, RocksDB. You plug in your own. And at first, that sounds awesome. People really want to use a C-based solution. They have this preconceived notion that C is always going to be faster. And next thing you know, you find yourself troubleshooting really difficult CGO problems. And so if there's only one takeaway, it's to heed the advice. If you're thinking about using CGO, don't be like me and think, I work with really smart people. We're going to figure this out. Just try and find a non-CGO solution. So when you turn back to looking at your pure Go options for key value storage, BoltDB is the first one you're going to come across. It's known for its simple API. It's going to be working with a single file, and it's a memory map B tree. Now, another one you might consider is Go LevelDB. That's also out there and it works very well. But I was looking for something simple. I wanted to get back to the roots of just something very straightforward and simple. And BoltDB was the opportunity to do that. So the idea was, what if we built an LSM, which is a log structured merge tree, and we did it on top of Bolt? So typically, log structured merge trees are going to have sorted strings in various memory or files. Instead of doing the low-level file IO ourselves, we're going to continue to use Bolt for that. And the idea is that's going to improve our performance for the cases where we have random index updates coming in, which would be slow if we're updating a single index in place. But we can now make that faster by writing each individual batch into its own BoltDB. Now, once we do that, of course, we have multiple BoltDBs, and we have to, when you're doing reads, we have to be able to read and seek across multiple BoltDBs as well. So how did we make it work? Well, the Bolt API is very simple. There's basically 4 constructs you need to worry about. The DB itself corresponds to the file. There's a transaction, which lets you do atomic writes and also do snapshotted reads. BoltDB has support for multiple buckets, even nested buckets within buckets. And of course, there's a cursor to let you fast seek around in the file. So what do we come up with? Well, with Cellar, which is the wrapper above Bolt that's going to do this LSM technique, we map the following construct. So the DB now corresponds to a directory containing a bunch of data bolts and one metadata bolt. We have a transaction object, and now each new write transaction is going to be responsible for creating a brand new BoltDB. And then we're atomically going to swap that into a list of active bolts that we maintain. Now, one thing we gave up in this API was BoltDB has support for multiple nested buckets. We've ripped that out for now, and we support just a single bucket. It's something we could add back in if people think this is interesting. And finally, we also have the cursor object. And as I mentioned, we have to sort of navigate through the multiple files to do that efficiently. So what does the code look like? We haven't looked at any Go code yet. This is code that would open up a Cellar instance. It's very much like the Bolt API. The open is going to take 2 things. So the first is a path, and the second is an options, which in this case, nil is a perfectly valid default options. Now let's say we wanted to write some data into this. Again, we're going to follow the same pattern that Bolt uses. We're going to have this update function. And inside of that, we're going to write a single key, in this case, K and V. And behind the scenes, what happens is we now have a new Bolt on disk. And we also have a slice that's keeping track of all of these BoltDB instances. So that was after one transaction, we have one file. If you run 2 more transactions, you're now going to have 3 bolts on disk. And you might see where this is going. That's fine as it stands, but eventually, you're going to have too many bolts on disk, and it's not going to perform very well. We sort of expected that and saw that coming. The nice thing about this is we can now merge together multiple smaller bolts into larger bolts. And this is going to be efficient as well, because we're going to be able to do an in-order traversal of all the items and write out a brand new larger bolt in sequence. Even better, we can concurrently do that, again, while the new writes are coming in, but also have multiple merges going on at the same time. So when that completes, we'll slowly have fewer bolts. And when it eventually consolidates everything down, we'll be back in this great state where we have a single BoltDB, which is going to give us the query performance we're looking for. Now, there's one other tool I'm going to pair with this. I don't have a great amount of time to go into it. It's called MOS, which stands for Memory-Oriented Sorted Segments. So the idea is to do the same LSM-teak, but totally in memory. So this is going to allow us to queue a bunch of things up in memory while we're waiting for things to be written out on disk. Again, a good KV store may do this for you automatically, but a very simple, tightly focused one like Bolt is not going to do it for you. So by putting these two things together, we get an architecture that looks like this. This is the MOS and Cellar combination. Multiple threads are coming in, building batches and writing data. Those are going to get sorted by MOS as one of the steps. That sorting can take place independently, so there's no locking going on. MOS is going to take these memory slices, and again, it's going to allow us to search across them even at that time before we've even handed them off to Cellar. But at a certain point, when Cellar's ready, it's not blocked on writing. We're able to move a whole segment down to Cellar. So as you can see, data is going to move into MOS, be searchable right away in RAM, and then eventually be moved out to disk, and then be efficiently searchable as a single bolt eventually. We have done some benchmarking. Again, it's probably very difficult to read because of the color choices. The first chart showing BoltDB indexing throughput versus MOS and Cellar. As you can see, it's about a 5 or 6 times improvement. Again, this is under our workload of indexing Wikipedia articles. And so with that, I'm going to lose my slides. So we've also measured the query performance, which I can just summarize as what you would expect. It's not as fast as a single bolt, because that's going to be the fastest scenario. Once you have multiple bolts, you're going to see a degradation. But again, that makes this KV store more useful for workloads where you have continuous indexing going on. So all the code's up on GitHub. If you think it's interesting, reach out to me, and we'll carry the experiment a little further. Yeah, thank you.